So okay. What I have to do before I do the anomalies is I have to do a little path integral development of currents. Currents, another theorem using path integrals. So the first thing I have to do is currents in path integrals. See, what you can always do is you get the Feynman rules and you do the usual derivations. This is a trick that lets you do many things all at once. So let's imagine that J mu is some current that you're interested in. You know, so for example, J mu is maybe psi bar, gamma mu psi. Okay, there's our typical curve. We're going to add a V mu is going to be some external source which will use it as a tool. Okay, so just like we added J phi to the Lagrangian, we're going to add this. So Z, when we do the path integral, could be a function of these external sources. So it's some d phi e to the I integral d4x Lagrangian minus j phi minus v mu j. Okay, so don't, I know I sometimes drop indices. That j is not j mu. Okay, that's the j that we use to take matrix elements of phi. Okay. So we do that. Then if we want to take matrix elements that involve the current, we can differentiate with respect to this background field V mu. So let's define J mu of x is I over Z of J, the variation of Z with respect to V mu. And we said V is equal to 0 at the end. Okay, so this then is something that is the response of the current J, and we then take further matrix elements. Okay, so if I want, for example, J mu, time order product of J mu of x, phi of y, 1 phi of y2, I would take further differentiations, I squared delta delta of j of y1, delta j of y2 of j bar mu of x. Okay, so basically, and you then set the other j's. You can get any of the matrix elements that you want by differentiating this guy. Okay. Everyone remember those tricks? I mean, if you want to just see an example, if I take J is psi bar gamma mu psi, that's put an E there if I want for the real electromagnetic current, and the Lagrangian minus V mu J mu then turns into, for fermions, psi bar I d mu plus E v mu gamma mu psi minus m psi bar psi. So this enters the Lagrangian just like an A field, just like a photon field. And so then if I want something that the matrix element 0 time ordered product J mu of x psi at y1 psi bar of y2 0, I just play these path integral games. I differentiate it with respect to one, with respect to the other, but it's just like the matrix elements that we had with photons. This would turn into I SF of y1 minus x E gamma mu SF of x minus y2. Here's the vertex that you're after, and you drop the propagators. Which you always do with these Green's functions, and you get the matrix element that you wanted. Okay, so that's how you would take this matrix element with that current in it. Okay, comfortable enough with that? We're going to use that in our test of symmetries. Okay. The next thing is path integrals and symmetries. Okay, so what we're after is we're going to reproduce an advanced version of Noether's theorem. So let's imagine some symmetry. If the symmetry, let's say, is phi I goes to phi prime I, which is phi I plus some little epsilon, some function of phi. There might be rotations in phi space parameterized by some small angle epsilon. Okay. Then, if that's a symmetry, then we then try, the way you get Noether's theorem the typical way is you let epsilon goes to epsilon of x. So this now turns into some epsilon of x. You define, well, you define the current is the variation of the Lagrangian in terms of phi primes with respect to d mu epsilon of x. Okay. That's the way you calculate the Noether current. Okay. And the reason that this is the Noether current is that the Lagrangian of phi prime d mu phi prime is the Lagrangian of phi d mu phi plus at most j mu d mu epsilon of x. Okay. This is the statement of the invariance of the Lagrangian. if epsilon is a constant, the Lagrangian is invariant, right? So if epsilon is a constant, this guy vanishes, and the Lagrangian is invariant. And then the usual method usually use equations of motion to show that d mu j mu is equal to 0. Okay, that's the way I did it. The first time I did it is using the equations of motion at this stage, and it basically comes from the fact that for a small variation, the equations of motion tell you that all variations of the Lagrangian change. So this is the only possible one, and so the equations of motion are basically gotten by integrating that by parts. Okay, so that's the usual pathway. And now we turn on the sledgehammer, the path integral. Let's do a path integral version. Okay. In doing this, I'm going to do the trick I did before. Is, I add v mu j mu to the Lagrangian. Then from this definition that I have, j bar mu of x is I variation of log z respect to v mu. We change that around to integral form. By the following. If I take log z of v mu plus some delta v minus log z of v mu. That's equal to minus I integral d4x j bar mu of x delta v mu. Okay, and let me just put primes on it. Clearly it's an integration variable, it doesn't matter, but for my next line I need to, it looks better that way. Okay. This follows from the usual functional differentiation that delta v mu of x of some delta v nu of x prime is g mu nu delta 4 of x minus x prime. Actually, so if I basically taking this variation here, that variation brings down this j bar. So it's the same as usual differentiation, except that it's a functional differentiation, so you get this extra delta 4, but it's the same as the upper derivation there, the upper definition. So that's the upper is the differential form, the lower is the integral form. Okay. Then, so now we choose delta v mu is minus d mu epsilon of x. Okay, so the formula that sits there is log z of v mu minus d mu epsilon minus log z of v mu equals minus I integral d4x prime j bar mu of x prime. I need d mu epsilon of x, which, seeing something like that, you always integrate by parts, becomes minus I integral d4 x d mu j bar mu of x times epsilon of x. Okay. So all of this reduces down to our test of symmetry. If z of v mu minus d mu epsilon equals z of v mu, we get that d mu j bar mu equals 0 for all matrix elements. Okay. So our test of the symmetry is then this beast right there. Are those two path integrals the same? Okay. Well, we'll see that that's very similar to Noether's theorem. So let's apply it. Okay. Z of v mu minus d mu epsilon is integral d phi e to the I integral d4x L of phi minus v mu minus d mu epsilon j mu. Okay, but if we go back to where we started in Noether's theorem, if we have d mu epsilon times j and L of phi, that's the same as phi prime in the Lagrangian in respect to phi prime. So if we come back down here, we see that this is, if the Lagrangian is invariant, this is the integral d phi e to the I integral d4x L. It's now phi prime d mu phi prime minus v mu j mu, which looks almost like z of v, because I've now got phi prime. And if we just do the normal change of variables, we're integrating over all phi, so that's the same as integrating over all phi prime. E to the I integral d4x L of phi prime d mu phi prime minus v mu j mu if d phi prime equals d phi. And so then this is equal to z of v. Okay. So it looks like we've reproduced Noether's theorem. given the invariance of the Lagrangian, we've passed our symmetry test, so all matrix elements are there. The trick is we now have two conditions. One is the usual Noether's theorem one, invariance of Lagrangian. That's what Noether would say. But the second one is the invariance of the path integral measure. This makes sense that we would do that. However, it turns out that this is a more stringent condition. So in quantum theories, require both and the anomalies are when one is satisfied but two is not. Okay, so these are things where Noether's theorem lies to us. Lied to us, and it's not a quantum symmetry. Okay, so that's where we're headed. Okay. Okay, questions? So what I'd like to start with is I'm going to start with the trace anomaly. Okay. The trace anomaly is going to be done in the context of QCD. And what I'm going to do is I'm going to integrate out the heavy quarks. Okay, and by integrating them out, we know that their effects go into only changing the coupling constants and effects that go like 1 over the heavy quark squared. Okay, so they've been removed from my theory. What's then left is the light quarks. So the Lagrangian is minus a quarter f squared plus psi bar id slash psi minus psi bar m psi. Okay. And we'll do some phenomenology to end up showing you that the mass of the up quark is about 4 MeV. Mass of the down, about 7. Mass of the strange quark is about 100 MeV. But the mass of the proton, of course, is 940 MeV. Proton nucleon. So the first approximation may be to consider these guys as small, and we run into an issue. The issue, in fact, we can separate how much of the mass of the proton comes from the quark masses, but that's not a story for today. So the first approximation, we can set these masses to 0 and then expand around that. But if m is equal to 0, then there's no scale in QCD. No in the Lagrangian of QCD. So the issue is going to be, how can you get any masses in a theory that doesn't have a scale? And you can make this much more formal. So here's the formal way of doing it. Let's do scale invariance. Okay, we can make this based on a symmetry. We let x equals lambda x prime, then d4x is lambda to the fourth d4x prime. So we're just going to scale all our coordinates. D mu goes like 1 over lambda d mu prime. We'll also scale all our fields. We'll take a mu of x equals lambda minus 1 a mu of lambda x. So we're making a scale transformation on the A fields and a scale transformation on the fermion fields. Is defined as lambda to the 3 halves I of lambda of x prime. Okay, so x is lambda of x prime, so we pull out an overall factor and then we rewrite it in terms of x prime just by definition. Okay, so it's the same point in space. Then the action, which is the integral d4x minus a quarter f squared minus, well, actually let me write out the terms individually. We know what that one is. So it's the integral d4x prime lambda to the fourth. That's changing the coordinates. I get minus a quarter f squared at lambda x prime is with a 1 over lambda to the fourth. 2 of them come from the derivatives and 2 come from the lambdas. Plus 1 over lambda to the fourth psi bar d slash prime psi minus 1 over lambda cubed psi bar m psi. Okay? So if the mass terms weren't there, this would be scale invariant. The mass terms break the scale invariance. So m equals 0 implies scale invariant. All right. The other term says there's a conserved current. The conserved current is the dilaton current. Let's just state it that it is. Okay, here's what it is. The dilaton current mu is the energy momentum tensor with an extra factor of x. And that is d. Okay? So if you take the divergence of that, d mu j dilaton mu, well, there's 2 terms in that. The first term is d mu t mu nu x nu. The second term is t mu nu d mu x nu. This is just g mu nu. The first term is of course 0 by energy momentum conservation. The second term is not. This is the trace of the energy momentum tensor. Let's look at what the energy momentum tensor is. You construct the energy momentum tensor. T mu nu is the following. T mu nu is f mu nu minus a quarter g mu nu f lambda sigma And actually that first term's wrong. There's too many mu nu's. There's f mu lambda, f lambda nu. There's mu and nu is the same, but contracted over. Then there's a term that's I over 2 psi bar gamma mu d nu plus gamma nu d mu psi. And there's a term minus g mu nu psi bar I d slash minus m psi. Okay. The last term can be just dropped. And just drop it by the equations of motion, because we're going to use the equations of motion. This term, if you look at t0, 0 gives you the 1 half e squared plus b squared piece. The t0i gives you the pointing vector. So all the usual results are contained there. Okay. And if I take the trace of this, t mu mu, the first term is 1 times f sigma lambda, f sigma lambda. The second term gives minus d over 4, d being the number of dimensions. And the next term here becomes I over 2 psi bar, no, forget the 2, d slash psi. Turns into m psi bar psi. Okay. So we see Noether's theorem telling us correctly something, looks like we're telling us correctly something here. We have the symmetry, scale invariance. We have a conserved current, which is the dilaton current. The divergence of that is the trace of the energy momentum tensor. The trace of the energy momentum tensor is 0 if m is equal to 0, which was our symmetry condition, and it's non-zero if it's not. So we have both the symmetry and the symmetry breaking explicit there. So there's our symmetry. Okay. Well, there's a problem with this. Okay. In general, if you take some particle's matrix element of t mu nu, okay, that is equal to p mu p nu with some normalization. In non-relativistic normalization is 2 over 2m, because then the matrix element of p t0 0 p is just the mass. Okay. In our normalization, often the one we use, n is 2 over 2e, but that doesn't matter. For the argument, it doesn't matter, but independent of the convention, then if I take p t mu mu p, that's n mass of the particle equals 0 if t mu mu is equal to 0. So if the trace of the energy momentum tensor is 0, then it says that all particles Okay, so in QCD that would say that the proton is massless. So we end up with a funny feature. The rest of our phenomenology tells us these quark masses are small. The up and down masses supposedly go into the proton. In the MeV range, the proton's mass is a GeV. If the quark masses were there, it would be proportional to a few MeV, but it's not. So what's going on? And the answer is that, again, this theorem lied to us, that this is not really a symmetry. Okay. And so the question is, so let's just write it here. Scale invariance is not a symmetry of QCD. Okay, and the right statement will be the following. Now, let me just give it to you. Is T mu mu is the beta function of QCD over 2G F mu nu plus sums over the quark masses mi psi bar I psi I. Okay. So the usual things that we saw by Noether's theorem are there, but now here's the anomaly. There's the anomaly. This is the gluon field strength tensor. Comes with the beta function of QCD, and it doesn't vanish as the quark masses vanish. Okay. So that's our anomaly. Okay. I'm going to give you 3 derivations of it, and clearly not all today. We'll work out the path integral version in some detail. We'll hand wave our way through the Feynman diagram one, and then we'll do a simplified derivation that gets you that coefficient exactly with very little work, almost no work. Okay, and by the end you'll see what's going on, hopefully. But in a sense, you can already start seeing it. So let's get you the answer so you can start seeing it. Is that the fact that it's the beta function there? The beta function tells you how the coupling of QCD depends on scale. But the fact that the coupling of QCD depends on the scale tells us that QCD isn't scale invariant. The scale enters through the definition of the coupling. So even though the Lagrangian was scale invariant, somehow the renormalization procedure, renormalization itself, brings in a scale through the running coupling constant, and the fact that it's the beta function sitting out in front determines that. Okay, so let's do it. Okay, well, I'm going to do 3 ways. The first way I'm going to do is the path integral method. Okay. And since I set you up on the path integral measure, I'm going to look at rescaling the fields. Okay. So in fact, I'm just going to do the fermions. The gluon parts are the same, and we'll be able to hand wave the contribution later. Okay, so the symmetry involved the rescaling. We had psi of x. Here I'm just going to look at the overall rescaling. So let's make it minus alpha of x over 2 psi prime of x. Okay, that was the rescaling of the field. And what I'm going to check is whether the measure is invariant under that. And it seems like it should be, d psi prime, d psi is the same. So if you change variables, so normally if you do dx1 up to dxn, and from dy1 up to dyn, the change of variables involves the determinant of the dx dy. So that determinant factor is the change of variables. What that tells us for our case is if I have the integral d psi of x, the path integral d psi bar, that's what sits in my path integral. That's d psi prime, d psi bar prime, times the determinant of e to the minus alpha of x. Okay, there's a 1/2 for the psi and 1/2 for the psi bar. Okay. Now, in what I've always done, and what we almost always do, we say, well, that's just a number. The number doesn't make any influence on the path integral measure, on the path integral, so we just shove it away and make the change of variable. And the person who noticed that's not always true was Fujikawa. Okay, and so what follows is Fujikawa's analysis. Okay, he said, let's check this by doing a gauge invariant regularization. Okay, and this is it's a funny one he chose, but it's okay. It makes the calculation easy for us. We're going to take the determinant of e to the minus alpha of x and convert that into the determinant of e to the minus alpha of x times e to the minus d slash over m squared. And so let's put that in brackets there. Okay. So this is fermion, so that's why he's using d slash. D slash is the covariant derivative, is d slash plus I g a lambda a over 2. And that's slashed. And the idea is that this removes the high momentum modes. Okay, so if you then take m goes to infinity, so let's put a limit out here, m goes to infinity, we would normally tend to agree with that statement, right? That seems innocuous. Okay. We then convert this using our standard tricks, e to the integral d4x, trace of x alpha of x log, log is already taken. I don't need the log because the determinant of that is e to the trace log, but this is e to the something, so it's e to the trace of that. e to the minus d slash over m squared. Okay. Right. Now, what we do is we pull out our heat kernel again. Well, heat kernel is x e to the minus tau, some call it script d, x, and we have that expansion for that. This sits in that form. The script d is d slash is all right, let's just write it out here. D slash plus I G A slash A lambda A over 2 D slash plus I G A lambda B over 2 Okay. The goal is to put this into our standard form of d mu plus sigma, and so let me just tell you the ways to do this. There's gamma matrices here. You write the product of two gamma matrices as the commutator plus the anti-commutator. The commutator turns into GAB. The anti-commutator turns into sigma mu nu. And we end up with a bunch of terms. If I do this, I have gamma mu, so there's a d mu is d mu plus gamma. Gamma mu is just IG lambda A over 2 A mu. So that's the easy one. And sigma is 1/2 sigma mu nu IG lambda A over 2 FA mu nu. Okay. And if you'll let me just complete this thing, we then do the heat kernel expansion. We write the heat kernel is, we had I e to the minus m squared tau over 4 pi d over 2. Tau to the d over 2, 1 minus tau sigma plus tau squared times all that stuff. 1/12 d mu d nu d mu d nu, etc. Okay, so in the interest of time, I'm not writing it out. The things to point out is that this m equals 0. There is no mass in those equations. This tau is 1 over m squared, because that's what happened up here. Up there, d slash over m squared is tau, capital D. And so this is tau to the, this is a factor of m to the 4th when it's done. This is 1 over m to the 4th. The trace kills this term and it kills a bunch of other terms, but it keeps the leading pieces. So if you add it all together, the trace of x e to the minus d slash over m squared x, that guy, is 3i m to the fourth 4 pi squared plus I g squared over 48 pi squared f a mu nu f a mu nu. The m to the fourth term comes from the 1. This guy is f mu nu. There's also a sigma squared term that's an f mu nu. But if you do all the algebra, it comes out to be that. If we just had the overall constant, we would have just thrown it away. That's fine. But here's a non-zero f squared sitting there, so that change of variables wasn't allowed. So here we then see that we have an anomaly. Okay, the path integral measure, the change of variables, leads to a field-dependent term that comes from that. Okay? So let me stop there. I'll come back. I'll quickly review what we did at the start next time and convert that into the anomaly equation, and then do 2 other ways of doing it. Okay? Is this blowing you guys away, or is it understandable? I can't tell. I'm not getting many questions out of you. You're not even answering that. Okay. What?
I'm not awake yet.
All right. Well,